Nash equilibrium here, right? F4 is Nash equilibrium here. So because you can see working with this table, you can see player 1 and player 2, both of them have no practical deviation. So F0 is Nash equilibrium. So that's hopefully clear for all of you. And then I argued that even if F0 is Nash equilibrium, it is not really a reasonable outcome. Okay? So let me briefly repeat my argument again. So here, player 2, his decision O is best response to player 1's decision F here, because if player 2 chooses O here, then his payoff is 0, right? But if player 2 chooses I here, then outcome will be again 0 for him. So both of them, I and O, both actions result in the same payoffs. So player 2 is basically indifferent, and so actually player 2 is indifferent, and for that way we can say that O is best response. Okay? And player 1's action F is also best response here. Actually, trivially, I can say, because actually player 2 will choose O, and that ends the game immediately. So actually player 1, according in this equilibrium, in this case, player 1 will have no chance to make any decision actually. Okay? So it does not really matter whether player 1 chooses F or A, because that moment of choice will not happen for player 1. Okay? Player 1 will has no, basically this node will be not reached in this case. Okay, so player 1 is best responding to O, and player 2 is best responding to F. So that's basically the reason why F0 is Nash equilibrium. Okay? But however, okay, so far so good, but here we ignore very important thing here, and that is what we have ignored so far is player 2's choice may change the mind of player 1, which result in the change of player 1's action. Okay? So when we argue that player 2's action O is best response here, what we implicitly assume here is even if player 2 chooses I here, it does not change player 1's action here. Right? But that is clearly not true, right? I mean, in dynamic game, every player has to be very careful about that his or her action may change other players' action in the future, obviously. And here, clearly, if player 2 chooses I, then player 1 will think about his action more seriously than before, right? And he will find out that actually F is not a best response if the game reaches to this place. And actually, indeed, player 1 will find he will have to choose A here. Okay? And so that's the reason we can say F4 is not a reasonable outcome. Player 2 totally ignores the possibility of his or her changing or affecting player 1's decision. Okay? Okay? So then the correct way to solve this game is, as we discussed before the break, backward induction. Okay? So player 2 has to consider both cases, O and I, what happens in the future after he chooses O and also after he chooses I. Okay? If he chooses I, then the game will reach this case. Then player 1, he is rational. Player 1 is rational. So player 1 has to choose A here. If this part of the game tree is indeed reached. Okay? And then in player 2's perspective, that means player 2 understands that if player 2 chooses I, then player 1 will choose A. Okay? And that results in payoff equal to 2 for player 2. But if player 2 chooses O, then the game ends immediately and payoff for player 2 will be 0. So given that player 2 takes into account that player 1 will choose A if player 2 chooses I, given that player 2's optimal choice here is actually I, because 2 is larger than 0. Okay? Any questions? I mean, if you think something is unclear, then you have to ask. I mean, it's very likely that your friends next to you is also confused. Very likely. Okay? So if you indeed ask some question, actually that is beneficial to everyone here, basically, and it's 80%, I believe. So if you think there is something unclear to you, then you have to ask. I mean, no one will blame. Okay? Actually, you know, everyone, most of you, of your friends will be happy actually if you ask some question. Any question here? I mean, you know, sometimes the best question, one of the best questions is just to ask, explain everything one more time. That is totally okay. I mean, if you think that is what you want. I mean, you know, asking question has a lot of positive effect. Of course, you know, it is really helpful for you, all of you, to follow my lecture. Okay? I mean, you know, clarify something, clarification of some points is always helpful for you to learn everything correctly here. That is clearly the first positive effect. And the other positive effect is by asking questions, you can help me to have the correct expectation about your class here. Okay? I mean, if you don't have any question, you know, the only thing I can assume is, you know, okay, you are following very well, and you know, and that may result in okay. So if you are indeed following very well, everything okay for you, that's okay. I mean, but if that's not the case, then maybe I can have some mis-expectation about you in this class that, you know, that is not really good for both of us. Okay? So, you know, asking question has a lot of positive effect. So I really encourage you to ask any question if you have anything to ask. Okay, so backward induction. So so soft-gain perfect equilibrium is basically almost you can say that soft-gain perfect equilibrium, which I will introduce you shortly, is basically almost equivalent to the idea of backward induction. Okay, so you know the outcome you can get by backward induction, like we did here. That outcome is almost always coincide with soft-gain perfect equilibrium. Okay, so but before we actually talk about soft-gain perfect equilibrium, I'd like you to introduce you one more concept, one more idea here. Okay, so far we have focused on pure strategies only. Okay, in every examples we have discussed so far, we just shut down the possibility of randomization. Okay, but of course, as we did for normal form game, we have to allow randomization of each players. Okay, so it is totally okay for each player, to randomize whenever they can. Okay, especially if they think randomization is good for them, maximizing their payoff. Okay, so we would like to allow them to randomize. Okay, so a pure strategy of player I is basically specifying which action to take at each node, right? So for example, in this case, player 1 has two pure strategies, A and F. Player 2 has two pure strategies, O and I. And mixed strategy is nothing but just, okay, so that's pure strategies, but they can also randomize actually, right? Instead of choosing either F or A with probability 1, alternatively, player 1 can randomize both actions with some probabilities. Okay? So we like to allow player 1 to randomize. That means we have to expand our notion idea of strategy allowing any randomization. Okay, so then behavior strategies, I'm going to use the behavior strategy, the term behavior strategies, and that is nothing but strategies that allow any randomization at each place of the game tree. Okay, so player 1's behavior strategies here actually, is any randomization between over A and F. Okay, so a behavior strategy of player 1 here has to specify probability of choosing F and probability of choosing A. Okay, so that's what I mean by behavior strategy of player 1. And if you specify these two probabilities, that basically specify every randomization that player 1 can do in this case. Okay, because basically there is only one place that player 1 can move. Okay, so behavior, okay, expanding the generalizing and extending the notion of pure strategy. From now on, we allow randomization, okay? And allowing randomization, a behavior strategy of player 1 has to specify probability of choosing F and probability of choosing A. Okay? Okay, what about player 2? So allowing randomization, player 2's behavior strategy has to specify probability of choosing O and probability of choosing I. Okay? And we are going to use this notation to denote mixed strategy. So sigma 2, that means behavior strategy of player 2. And so this thing here means what is probability of choosing O by player 2 at T0. Okay? If this number is equal to 1/2, if we write sigma 2 O T0 is 1/2, that means at T0, player 2 will choose O with probability 1/2. Okay? So here we specify the place, the node we are concerning, and this is the action we are concerning, and the everything here, the whole thing here on the left hand side, that is probability of player 2 choosing O at T0. Okay? And similarly, for example, this is, so T1 is here, this node. So this number is, let's say, if I write this equation, that means player 1 will choose F at T1 with probability 1/3. Okay? So behavior strategy of player 2 has to specify this number and this number, and behavior strategy of player 1 has to specify this number and also this number, which is 2/3 in this case. I mean, if this probability is 1/3, then the other probability has to be 2/3. Okay, a little bit more example. So what about this game? So here, pure strategies of player 1 is any number between 0 and 1, right? So if we allow player 1 to randomize, that means player 1 can choose any probability distribution over 0 and 1. Okay? And then player 2's behavior strategy. Okay, so player 1's behavior strategy has to specify that distribution over 0 and 1. And player 2's behavior strategy has to specify probability of choosing Y, conditional on player 1's choosing S1, and also probability of choosing N, conditional on choosing S1 for any S1. Okay? So player 2's behavior strategy has to be able to tell for any possible choice of S1 observed in the previous case, observed in the previous stage, what is probability of choosing Y and what is probability of choosing N. Okay? This game is something we call centipede game. So here basically player 1 has 3 places to move, here, here, and here. And player 2 also has 3 places to move, here and here and here. And their behavior strategies has to specify what is probability of choosing S and what is probability of choosing C for any node of the tree. Okay? Okay, so now we are ready to define sub-game perfect equilibrium, which is basically the way we formulate the idea of backward development. Okay, so first of all, let me define what I mean by sub-game. So sub-game is a game I think it's better to begin with the example here. Okay, so this is a game, right? But let me draw that tree here. Okay, I think it's better to begin with simpler example here. The electric game first. Okay, so this is a game tree here with 2 places that a player can move. Okay? But for now, let's ignore this part here and let's focus on this part of game tree. Okay? So then, if you just focus on this part, ignoring here, then it is another game tree you can think of. This game is really trivial because player 1 choose either F or O, and that ends the game immediately. So it is very weird game in the sense that even if there is player 2 does not make any action here. But anyway, still, sounds weird, but still, this is just perfectly legitimate game. Okay? Player 1 chooses action either F or O, and that game ends immediately. If player 1 chooses F here, then outcome will be 0, 0. And if player 1 chooses O, then outcome is 2, 2. So that is a game which is a sub-part of the entire game. Okay? So in our language here, in our terminology, we're going to say that this part of the game, beginning from this node, is a sub-game of the entire game. Okay? This game has two sub-games. First, this is a sub-game, and the entire game is also a sub-game. Okay? So this game has two sub-games. And let's look at the game on the screen. So okay, so this is exactly the game tree you can see on the screen. Okay, so think about, for example, this part of the tree. Okay? And if you think the situation that begins from this node, then just ignore this part of the tree. Then this tree is another legitimate game tree with this node as the initial node. Okay? And this is just perfectly fine game tree such that player 1 moves first here, S or C, and then player 2 moves C or S. Okay? So this is this is, in other words, this is a sub-game of the entire game here. Okay? And of course, this is not the only sub-game. If you just focus on this part of the game tree, this is also a sub-game. And if you look at this part of the game tree, this is also a sub-game. Okay? Actually, in fact, for any extensive form game with perfect information, if you just, there is always a sub-game beginning from any node in the game tree. You just pick one node in the game tree, then there is always sub-game beginning from that node. Okay? Okay, so definition, more precise definition of sub-game is available on this page. So a sub-game of an extensive form game tree T is one that consists of a single node and all its successor in the game tree. Okay, so that is kind of more technical definition of game tree. But for example, but that's exactly So for example, let's look at any game, any node here, and if you just think about this node and four other nodes succeeding this node, then you can find there is a sub-game. Okay, so a little technical definition, but there's nothing really new there. I mean, once, as long as you understand, what we did on the board, then you can just totally disregard that technical definition of game, sub-game. Okay. So the idea is that, again, let me repeat one more time. Just choose any node in your game tree. Then there is a game soft game beginning from that node, right? So and you can find such a game tree, soft game beginning from any node in the extensive home game. Okay, so definition of soft game perfect equilibrium is like this. Okay, so a behavior strategy profile sigma is a soft game perfect equilibrium if the restriction of sigma to any soft game is a Nash equilibrium for that soft game. Okay, so again, a little bit difficult, a little bit complicated definition, but let's look at this game again as an example. So there is two soft games here, okay, and again, we would like to say a pair of strategy of player 1, behavior strategy of player 1, and behavior strategy of player 2. That pair, we are interested in whether we are asking whether any pair of these two strategies is a soft game perfect equilibrium or not. Okay? Soft game perfect equilibrium requires that restricting these pairs of strategy to any soft game is Nash equilibrium for that soft game. Okay? For example, there are two soft games here, and let's ask whether, let's say player 1, sigma 1 here is player 2 choosing O here, and player 1 choosing F here. Okay? So if this is soft game perfect equilibrium, then restricting this strategy in this soft game, for example, has to be Nash equilibrium for this soft game. Right? But this is clearly not the case. Okay, if you restrict attention this part of the soft game, this soft game, then there is only one player to move, and it is soft game, it is Nash equilibrium for this soft game only if this move maximizes player 1's payoff. Right? But clearly F is not maximizing player 1's payoff. In other words, player 1 has profitable deviation in this soft game. If player 1 deviates to O, then his payoff will be 2, which is larger than payoff here. So player 1 has profitable deviation, and in that sense, restricting our candidate of equilibrium strategy into this soft game, it fails to be a Nash equilibrium here. Okay? Let me repeat one more time. Okay, so we will say a strategy profile. So by strategy profile, what I mean by that is, just list of strategies of each player. So here, strategy profile has to specify player 1 strategy and player 2 strategy. Okay, and we will say this a strategy profile is a soft game perfect equilibrium if restricting your attention to each soft game, you have Nash equilibrium. Okay? So here we have two soft games, right? So in order to check whether this is soft game perfect equilibrium or not, we have to check whether restricting attention here, whether it is soft game, it is Nash equilibrium here, and also we have to check whether this is Nash equilibrium restricting our attention to this soft game. Okay, so there are two soft games. So let's see this part, this soft game first. Okay, so this is soft game, a soft game, very weird soft game, very simple and strange soft game, such that player 1 makes a decision, F or O, and then game ends immediately. There is no role of player 2 here. But anyway, still this is a soft game, so we have to ask whether this is Nash equilibrium or not for this subgame. Clearly, this is not a Nash equilibrium for this subgame, because in order to be a Nash equilibrium, all players must have no profitable deviation. I'm sorry, all player, right, must have no profitable deviation. But clearly, player 1 has profitable deviation here in this subgame, right? If player 1 chooses O, then his payoff will be 2. But if he follows the original plan, then payoff will be 0. So restricting your attention this subgame, you can see it fails to be a Nash equilibrium in this subgame. Okay? What about this? Okay, so there is this already shows that this is not a subgame perfect equilibrium. But what about, okay, so let me look at the other example. So now let's check whether this is a subgame perfect equilibrium or not. Okay? So here player 2 chooses I and player 1 chooses M. I'm sorry, it has to be O, right? Okay. A. Okay, let's check whether this is subgame perfect equilibrium. Okay? So again, we have two subgames, and restricting our attention here in this subgame, you can see this is Nash equilibrium for this subgame, right? Player 1 has no profitable deviation. If player 1 deviates and chooses F, then his payoff will be 0, which is smaller than 2. Okay? And there's only one player in this subgame, so that's sufficient to conclude that this is Nash equilibrium for this subgame. Okay? So this passes our first test, test 1. But there is another test we have to do. So we also have to check whether this is Nash equilibrium for this subgame. Okay? Indeed, player 1 has no profitable deviation, right, for the same reason. And player 2 also has no profitable deviation. Because, okay, so here the original plan is I, but if player 2 deviates and chooses O, then his payoff will be 0. But if player 2 sticks to the original plan, then his payoff will be 2. Okay? So deviating to O is not a really good idea. So in that sense, player 2 has no profitable deviation, and we already have checked that player 1 also has no profitable deviation. So this is sigma 1 and sigma 2 here is also Nash equilibrium for this subgame as well. Okay? So that is what I mean by, what I try to convey by this definition of subgame property equilibrium you can see on the slide. A behavior stretching profile sigma is a subgame property equilibrium if its restriction to any subgame is a Nash equilibrium for that subgame. If that's the case, if that's true for any subgame, we say that sigma 1 and sigma 2, or sigma in general, is subgame property equilibrium. Okay, so let's look at this game. So I'm going to argue that actually this is, so let's consider this strategy. I think maybe it's better to erase. Okay, so this is centipede game. And let's say we are checking the one I drew on the game tree is whether it is subgame perfect equilibrium or not. Okay? So in this strategy, according to this strategy, all players choose S whenever they have to choose something. Okay? Okay, so then let's check whether indeed this is, if this is indeed subgame perfect equilibrium or not. Okay, so there are actually 1, 2, 3, 4, 5, 6 subgames. Right? So there is a subgame beginning from this node. There is a subgame beginning from here. There is another subgame beginning here, beginning from here, beginning from here, and beginning from here. So there are 6 subgames in total. And let's look at this subgame first. Again, this is kind of really simple subgame, such that player 2 moves either S or C, and that ends the game immediately. Okay? But you can see here, player 2's choosing 6 is actually her best response. Because if player 2 chooses C, then outcome will be 5, payoff will be 5 for her. But by choosing S, she can get 6. Okay? So best response of player 2 is 6. So if you restrict your attention into this subgame, clearly this is Nash equilibrium for that subgame. Okay? What about here? The subgame beginning from this node. So we are looking at this subgame. Okay? So again, player 2 has no profitable deviation. We already checked that already. And let's look at player 1. If player 1 chooses C instead of S, then his payoff will be 4. Right? But if player 1 chooses S as planned, then his payoff will be 5. So indeed, choosing S is best response for player 1 in this subgame. And this is also subgame, this is also best response for player 2. We already have checked that already. So which means that restricting attention to this subgame, this one and this one, our candidate here of our strategist here is Nash equilibrium for that subgame. Okay? And you can repeat the same argument to show that it is also it is also Nash equilibrium for this subgame, and also Nash equilibrium for this subgame, and also Nash equilibrium for this subgame, and also Nash equilibrium for this subgame. Okay? So for any subgame, all players have no profitable deviation. Okay? So that's the notion of subgame perfect equilibrium. Okay, so why we are caring about subgame perfect equilibrium? Okay. So here is the idea behind subgame perfect equilibrium. Okay, so let's say player 1 finds himself here in this situation. Okay? And then in order to make a decision, in order to make a good decision, player 1 has to figure out what will be happening in this subgame after he chooses C. Okay? And then the answer should be the outcome in this following subgame has to be a Nash equilibrium for this subgame. Right? Why? Because remember that we have assumed that all players are rational. Right? And it is also rational, rationality is also common knowledge. Okay? And if we add one more assumption that all players have rational expectation, then we learn that the outcome has to be a Nash equilibrium. Okay? So the point here is that Nash equilibrium is kind of always reasonable outcome. One of at least candidate of reasonable outcome in any game. Okay? So if player 1 chooses C, and then player 1 has to expect that outcome will be at least, outcome of the following subgame has to be at least a Nash equilibrium. Okay? So Nash equilibrium is, we believe that if rational players play with each other, then outcome has to be one of Nash equilibrium. Right? So in the line of that reasoning, if player 1 finds himself here, and if he thinks what will happen if he chooses C here, then he have to think that the outcome of this subgame has to be Nash equilibrium for this subgame. Okay? And same thing for here. Let's say you are player 2 in this